is some historical story. So I, as far as I know, so Gauss is a really big guy, big shot in mathematics, and Riemann. So Riemann, I don't know his exact spelling, but Riemann is the is a student of Gauss, and then Riemann basically came up with some developed the area of information. Differential geometry. And this differential geometry eventually evolved into physics. Okay, okay, maybe it's not really necessary, right? So, so this information geometry is actually a important mathematical tool to develop the relative theory by Einstein. And so that's a big hit in physics. But in statistics, it's not well understood until, well, actually there's a big guy, R.A. Fisher. He's the one who used the differential geometry idea to develop the Fisher information. All this is actually a part of this differential geometry. And then there's a Japanese guy, Amari. He's the one who really, Amari, right? So he's a big shot in Japan, and he developed this. He makes the fundamental theory of information geometry, uh, uh, but uh, but I think that's very hot in Japanese statistical society, but somehow it's not fully understood outside Japan. Partly because his lecture is very difficult to understand. So I will try uh, to be more accessible to you because I'm a statistician. I'm not really a mathematician. So hopefully my lecture gives a better, instruction to people like us, right? Basically. So anyway, welcome. Uh, so so statistical model will so we use statistical model. When we say model, that means we need some kind of parameterization. So parameterize is more like XY type axis. And so we have a coordinate. Basically, it's a coordinate system. So coordinate system means that all these. If you know which coordinate, right, that means you determine the distribution. So each point is actually each point in this manifold is a distribution. Okay, and so the local coordinate system. So it doesn't have. It's not really Euclidean, right? We are talking about abstract type uh, model, and and so the second model M is said to be geometric regular when it satisfies regularity conditions. So there's a very mathematical deep concept to
Jay? Yeah, sorry to interrupt.
no,
Can you stop share and share again? Because
okay,
there is kind of a weird thing happen.
okay, will do. Okay, yeah, you more
Okay.
the key person in my research team, so I cannot really
Sorry.
mine this because
Yeah, thank you,
okay.
Jay.
Okay, but so I cannot really I don't have the ability to give the very rigorous mathematical treatment on this topic, but so it's probably your preference if you choose to investigate more on mathematics, but I will mainly focus on statistical meaning and how it can be connected with the statistical things. So basically, yeah. So yeah, so there's some kind of one-to-one mapping type idea, and so I think one important thing is support is common for, so we don't really, for example, uniform distribution between A and B doesn't belong to this class, right? So we want to be include regular. So we want to consider a particular class of model that this theory applies, and this particular class, one of the condition is that we should have a common support. And also, we need some nice property like is a smooth in theta and integrable, and we can exchange the order of integration and differentiation, right? And so that's something we usually use in deriving the Bartlett identity. For example, in my class yesterday, and the scope function moment of the scope function exists up to the third order and smooth in theta and Fisher impulsion matrix positive definite. Okay.
I have a question about the second.
Okay.
Like, what it exactly is? Like, I guess.
Yeah, you can ask ChatGPT. Okay. This kind of thing. Yeah. I don't know. Well, sorry. I didn't discourage you to answer your questions, but I don't know the answer. So you can ask if you're curious. So okay. So this is the major, this is the major theoretical concept. And so notation is we have a parameter is in parameter space and so d-dimensional, and C plus means that the notation. So notation is a little bit too much, but okay. This is we only consider positive subset. So positive, not so positive support. Okay, and C1 is a first order differentiable. And so L is okay. So the idea, okay, let me quickly talk or give you some. So okay, the whole idea, key idea is we want to do some projection, okay, some space. So okay, if you know the vector space, right? If you have a vector space, we know how to do the projection, right? Because if it's a vector, then we have L2 type. I mean, so that means we have this is actually so to define a distance, right? To define a distance, we need to define the inner product. And so this is for the vector case, no problem. And we can easily extend it to random variable because random variable is nothing but an infinite dimensional vector. Okay, you can view that way. So if it is a random variable, so now it's a random variable, then what is the definition of this one? So that's integration, I mean expectation. Okay, so the norm. So if the space is random variable space, that means we have a particular. So this kind of space is L2 space. L2 space with the distribution P. So that means the distribution, all the random variables that in this distribution belongs to this distribution. Okay. But then we have a subscript 0 to denote that this is actually mean 0. Okay. So then basically what do you mean by project? So for example, let me quickly talk about. So this is a linear space, right? So that is a span. So basically a span of p random variable, random vectors. Okay, so that is a space. Then how do you define? You pick any element here. So if you pick any element, then this element can be written as x beta, right? Because you can basically write the beta 0, beta 1, x1 plus beta p, xp. Okay, this is a linear space, and beta can, so beta actually determines the coordinate, right? So beta determines the which point of this linear space. And then now, so then how do you define this projection? So projection is the minimizer, right? Minimizer of the distance y minus certain random variable y star square subject to y star belongs to this is a linear space. Is it clear? Okay. So then basically this guy, how do we usually compute this guy? Is basically so that means we need here we need to talk about the expectation. That means we have to have a distribution, right? So distribution is P. This P. So this P is here, this P. So the reference distribution is fixed. And then we are talking about the random variables and talking about the norm, right? The L2 norm. And then basically we want to do a Pythagorean theorem. This is very well known, actually, right? So this is a Pythagorean theorem. And so, and then what is this? What do you mean by this? So what condition do we need for this beta star? Well, it should be orthogonal, right? So this is orthogonality condition in order to achieve this. So then that's how we, so every point, every line in this space is orthogonal to this residual, right? So that is a normal equation, essentially, normal equation in terms of a vector. So this is basically the Hilbert, projection theory in the Hilbert space of random variable. And we want to do, but here we are not really talking about the Hilbert space of random variable. The space we are talking about is a space of distribution. Okay, and that's more difficult because here the distribution here is fixed, right? So distribution is fixed here. But here is the space is a distribution. So that's a different story. And then so how do you define this two distribution? Okay, how do you define the distribution of the distance? How do you define? What do you mean by that, right? It doesn't make sense because if you want to do expectation, there should be a distribution that we are referring to. So then also, we cannot really use the Euclidean distance, right? And so that's why we want to introduce Kullback-Leibler distance. So it can be either this one or so we want to do some projection using Kullback-Leibler. That's the first goal of today's lecture. And the problem is these two we want to use this one as a distance measure, but they are not really distance, right? Because they are not symmetric. They are not symmetric. You cannot really exchange the P and P star. No. So that's why. So then basically the projection here is different from projection here. Okay. So it turns out that the projection, one projection we call E projection. The other projection you want to call M projection. So that is basically the big picture of the today's lecture. Any questions about this? So bottom line is we wanna establish a Pythagorean theorem, because that is the key concept in developing projection. And once you so the projection is so important, because whenever you talk about optimality in whatever the sense, right? You have a class, you want to define a class, and among the class, you want to choose the best one in certain criteria, right? Using a certain criteria. And so that is basically what we are going to do. And that's a really fundamental concept, because any problem in statistics, machine learning, AI, even all that area uses some sort of optimality, right? And so that is what we are going to address here. So, but to construct, so to derive this Pythagorean theorem, there's a lot of mathematical construction, which is too difficult. So I don't want to cover that, all the mathematical hurdles, because if you do, then we all give up in the middle of the way. So that I don't want to do that, and I will just give you, show you the goal. So it's like rather than top down, right? So mathematicians start with a concept and build until we reach the problem. But the problem is that if you do this way, you spend too much energy in the beginning, and you get lost in the middle of the way. So my preference is to start with this. What is the goal? And then to achieve the goal, what we need. And then to achieve this particular tool, what we need. And so I prefer to study it in a backward way, because that's more efficient, although it may not be really rigorous. Okay. So I think I already explained the meaning of L2 script 0. So subscript 0 means the mean 0. 2 means that second norm, okay? And P means the P theta means that the expectation we are referring to should be in that particular distribution, P theta, okay? And then this parameter, so this is a coordinated system, as I said. This is coordinated system. We want to define some sort of a tangent function, tangent space. And so idea is, okay, this is you take the log and then differentiation with respect to t, and then this line should pass theta at t equals 0, okay? So this, as a line of t, it should be differentiable, but it should pass what we are interested in, particular set. So the whole idea is you want to define tangent, and so the exact meaning is so how to do a tangent space. It turns out that the important concept is the scope function. As we already know scope function, and so I think the key contribution of R.A. Fisher is to recognize the importance of a score function in statistics. So in mathematical statistics. So one proposal,
Jay,
yeah,
I try to understand the space L.
okay,
So for every theta, we have a space L
yeah, right, that's right. So
because
thing-
the M is basically a space of distribution
right, right,
indexed by
right,
theta.
right.
And for every theta, you have a L2 integrable.
That's right, that's right,
That
right.
basically is a function,
Yes,
right?
that's right. So so this is one space, right? This is one space. And point is that for each different theta, we have a different space. So it's kind of moving from one theta to another theta. That's why it's so difficult. Because question is how we want to preserve this orthogonality when we change the theta from theta to theta prime. So that involves some concept of parallel transport and all these things. But turns out that in statistics, we don't need that concept. So, but anyway, this is, yeah, you're right. So this is one theta for one theta. So for each theta, we have a space. And then for different theta, we have a different space. The space moves, basically. It's like, I mean, in the physical world, theta can be, uh, I don't know, theta can be, if you think of time, t is time, then basically you have uh, each time you have basically space, right? And so that's how, well, I don't know, I'm not really expert in this physics, but point is, uh, uh, this L2 is just one space. And we know that we want to move this theta over and want to do projection for different theta as we move theta along.
We have a fixed distribution, right?
For
P,
fixed
P.
theta, right?
P and P prime. I'm looking into P and P prime.
Well, there's a line. So from theta to theta prime there. So point is actually, so yeah, actually eventually there's a space here. There's another space, and we cannot really arbitrarily move from one theta to theta. Actually, it should be E flat. So there's some. I will move on. So so there's a particular way of moving from one theta to another theta to preserve the metric, to preserve the metric. We'll see that soon. Okay.
Uh,
And
so
yeah,
Jay,
yeah,
can you go to yeah? So here, I'm trying to understand this T theta M. Uh, so this is like uh, an, a tangent space.
tangent space for a particular theta.
Tangent. Um, so what does theta T? So why theta is also a function of T? So it's a different T or oh, so you still take a differentiation with respect to theta, but you find a special direction of theta.
It turns out that the choice of theta t does not make any difference.
Okay, this notation log p theta parses t, the parses t is for theta is not for p, right?
So this is log just p theta x, right? So this is basically log density.
Okay, so the t is for p.
T no, t is dt. Okay.
Yeah. Yeah, I mean, so this notation P, theta, T. So
Uh,
T is the index of P or T is the index of theta?
okay. S- so so T is an index of theta.
Oh, okay.
Okay. So
Okay.
yeah, well, this is maybe this proposition may give you better idea. So even though this concept is difficult to understand, turns out that this tangent space is nothing but a linear space generated by the scope functions. Okay, and so here's actually proof to show the equivalence. We need to show this direction and this direction. Okay, and so that is the basically what the proof is easy, but so I will skip the proof. But the concept is uh, tangent space is nothing. So it is enough to use the scope function to discuss all uh, about the space.
This is for a particular theta, right?
So for particular, right, for particular theta, we have a space, but we have a basis function, t basis functions, and these basis functions will change with the different theta. Well, I can actually use, okay. So this is so let's pick any element. Okay, how to prove this? Pick any element in tangent space, right? And then by definition, this we can write this way. And then by the chain rule, we have this one. So that gives this expression, which is the span of S theta. Okay. So there's a type of S theta. And then and also, normalization. I mean, the normalization means because P theta is 1. So this one is equivalent to having the S theta is expectation equal 0, right? So so that means U is, which implies U is expectation 0. So that proves this direction. Right.
So that theta t is a function of t, right? So like that theta t is a function of t, and it's written that theta t equal to theta plus t. So is it like that uh for every theta or theta prime, so that function can be changed?
Yeah. I mean, which function are you talking about?
That for any curve that for any a, the curve theta t equal to theta plus t a is the tangent.
Okay.
So I'm talking about like in the previous one, so where for each theta you talked about like each distributions like theta prime. So for each theta there are some time points, right?
So for each theta, right?
Yeah. For each theta, I mean theta is a function of t, right? So for each theta t, like theta t, so theta t or theta prime t, so is that function will be changed, right? Like this function that theta t equal to theta plus t a, which has been written here.
I'm sorry, I cannot understand your question.
So I'm just talking about like that theta is a function of t, so that for each theta, I mean for each theta, I mean theta or theta prime or any other,
Okay.
is the the function is changing. I mean the
T change, right? If we change T, the theta will change.
yeah, I mean, and also like when we talking about theta t is a particular function and another theta prime t is another function, right?
Okay.
Okay, so he's talking, maybe I understand.
Yeah.
Basically, so we are talking about theta and theta prime, two different spaces, for example.
Okay.
He's saying here we have theta t is equal to theta plus ta. So it's kind of function. For theta prime will be another function. So that is his question, right?
Yeah.
Devarga?
That's another two curving vehicle. You have
Okay.
restriction in theta zero have to be specific theta.
Mhm.
You change another theta prime,
Okay.
that center have to be on that theta prime. something like this manifold. Theta, one theta t through this one,
Okay.
another theta through this one,
Okay.
another curve on the same manifold.
Oh, okay.
I think because of the continuum arise from the rotation, because the parameter theta is fixed value.
Yeah.
But I think the notation is quite slippery here because the function is expressed as theta.
Hmm.
I think they are different.
Yeah.
Yeah, but the function theta can vary every time.
Okay.
So I think the confusion arises from.
Okay.
Okay. Okay. Let's move on. And so the other direction is basically if you construct yeah, well actually I think the other way, but well you can check this proposition proof. And there's some basic concept like a tensor and Fisher information. So Fisher information is nothing but inner product of two score functions evaluated at that theta. Okay, and there's actually third order symmetric tensor, but this is not really important to our research. So this is a kind of a summary. So tangent space is this one, which and with this space we have a metric is a feature metric, which is inner product of two vectors in this space. Okay, and now let's move on to exponential family. So
Jay,
yeah,
so in the previous y t equal to L, so these are so t is a tangent space,
well,
right?
locally. So if you fix, okay, so for given theta, then for fixed theta locally, then locally you can view all the random vectors in this tangent space. Is actually belongs to this L2.
Yeah, but L2, so the tangent space should be a subspace, right, of L2 theta, Q theta.
Well, I don't know exactly, but there's actually some argument, some local approximation argument, but let's just pass this for now.
Okay.
Okay, sorry. Okay, so exponential family. Okay, so this is a very interesting, important concept from now on, because so when we learn exponential family, we don't really know why we consider this one, but it has a very interesting, information geometric connection. So basically, you have a certain surface statistic, right? And then using that, you basically construct the exponential distribution. And then this guy, we call cumulative geometric function, right? And also this has a very important meaning in physics. They call it free energy. And so if you view this one as a coordinate system, theta, then this kind of coordinate system can be called natural or canonical parameterizations. This is one parameterization of the exponential family. And now, one interesting property of this CGF, cumulant generative function, is that if you differentiate it with respect to theta, then you get moment, right? So basically, if you take the differentiation, so this is really important. So everybody can see this? Okay, so this is the key part. Okay, so basically, because if you differentiate this psi theta with respect to theta, then you get expectation of your surface statistic. And now I'm going to call this as eta. Okay, eta. And then because the point is that there's a one-to-one transformation between theta and eta. One-to-one. Because if you change your theta, then you change eta. Like if you, right? So theta could be something like this. So if you change mu, no, this is not really good. We'll have another example later. But if you change theta, then because of that, you change the mean of sophisticated statistic. So we can call this expectation parameter. And then let's construct the function, particular function written by this way. Okay, where so given eta, so we input eta, and then write. It turns out that if I construct this way, then we can show this. So then there's a very nice functional form. So that's why it is one-to-one. So if you given psi, right, using psi, you can construct another parameter, eta. And then from psi, you can construct psi star. And then this psi star can be shown to satisfy exactly same reverse operation. So this is actually a dual. So psi star is a dual function. So dual, so this parameter is dual. Okay, so this parameterization is dual parameter, dual relationship, and this function we call it convex conjugate. So psi star is a convex conjugate function of psi, or the other way too. Psi is a convex conjugate function of psi star. Okay. Because a dual of dual is dual. Original. Okay, dual of dual is original. So this is really a key part. So basically, we have a dualistic structure concerning the two coupled coordinate system at eta and theta. So like a mirror, right? So it's kind of distorted mirror. If you have one thing going on in one space, there's exactly same thing can be mirrored to the other space. And now we move on to another very important concept. So, okay. So consider a manifold of exponential family with this particular parameterization. And then let's consider two different transformation. First one is if you just make the this is basically you have a 2 point, and then you construct that convex combination, right? So if you construct convex combination, that create the whole family, right, as a function of t. If you choose move t, right, from 0 to 1, you basically create another family, which is indeed linear transformation of this in terms of log scale. So that is an interesting part. Well, because this is we start from exponential family, okay? So exponential family is nothing but linear, closed linear in the log scale, okay? So the geodesic, so there's some term called the geodesic. The geodesic is some kind of path. Okay, you create a path, but the path should preserve some some consistency. I mean, some property. So for example, if you in this exponential family, this particular coordinate system preserve the make some connection, right, in terms of log scale. Okay. So a geodesic, you can think of a geodesic means a line, okay, line of distribution. Okay, so it's not
Point, like in a convex.
so
2 points.
right. You have a 2 point and you want to connect a line, but so how to create a line such that their property doesn't change. So here, if you choose this particular right, so if you consider this family, exponential family, then turns out that all these element in this geodesic line, it belongs to the same exponential family. Nothing else, right? I mean, if it so that is kind of 1 point. So if you in the theta, and then another one is okay. Now we have a eta. Eta is remember eta is a dual, right? A dual of theta. And then now you consider a convex combination as of 2 etas. Okay. That means what? This is a mean, right? So, oops. Okay. Yeah. Sorry. So this is a so basically this is remember this is expectation of px for 1 theta, and this is expectation of p in another theta basically. Okay. And so that means there's a so so there's a path. So in the theta, so the line, right? The line connecting set from theta 1, theta 2 has some connection with the line in terms of eta. Okay. And turns out that this is another line. So because of this property. Okay.
Theta 1 and theta 2 belongs to the same coordinate system, right?
So we are talking about actually dual connection. So one connection is E connection. E connection means a log scale, and the other one is M connection. And in terms of the expectation. So the sum manifold satisfying 6. So this one is called E flat, where E stands for exponential. And subphonic manifold satisfying 7 is called M flat. M stands for mixture, because this one is indeed a mixture distribution. So, so basically we have introduced 2 different criteria of straightness or flatness in the manifold. One is a primer, and the other one is a dual. Okay. So we can call it, this is actually the key concept of dually flat. So because this is more like a theta scale, this is eta scale, right? And so whatever we have a line here, there's actually corresponding another one, right? So it's like a mirroring, right? It's like a mirroring.
I have one question.
Okay, sure.
Is the line not a curve? Is theta of function of t
Okay.
is convex combination of that. What is from theta? We form a straight line, but that curve does not correspond also straight line in this.
No,
theta
no,
space,
right, no.
And this line and this line did not be
Exactly.
representing same curve in manifold, right?
Let me I think okay, maybe there's some kind of a summary. I think you are talking about this one, I guess. So if you, let me just,
Oh, I think that's one.
right?
The straight line in E structure is not same as straight line in M structure.
No,
Yeah, okay.
not at all. Okay. So we have basically two paths, two different passes. But let's okay. But yeah, well, in the very big, so to be honest, when I was I studied this concept several years ago, really work hard, but I really couldn't figure out because it's so difficult and so many new things I have to study. But I now realize that this is actually good because then others cannot easily understand, right? I mean, right? If this is easy to understand, then everybody else can also very easy, and then everybody can be jump in and solve a problem. Then really it's like a AI, right? So everybody doing AI. So how can we really, beat, so yeah. So anyway, I think so that's another reason why this is promising because this is not easy.
So,
Not
Jay, can I look at this E flat and M flat? So the previous page, page 10.
page 10.
Yeah, page 10. So 6 is E flat.
Mm,
Okay, so this is on the original
right,
theta scale.
right.
Because take log, so it's called exponential.
Mhm.
Okay, and then the next page 7 is directly combination.
Mhm.
So it's called M flat.
And flat, right?
Okay.
So I will have actually a small example soon.
Mhm.
Here. Maybe, yeah, maybe I will just use this example to explain.
I have one question. So you introduced tensor, so I could not get the connection. What is tensor doing here? Like,
You don't have to know that. I don't know much about tens.
oh,
Yeah. So yeah, well, currently it's just the dual flat and all this is enough for understanding the Pythagorean theorem. So let's use this example. So Bernoulli, we know everybody knows Bernoulli, right? So okay, so the eta is okay. Let's use bx equal x. So that means eta is just x, ex. So then basically x is a Bernoulli eta, right? So then density, okay. So density is what? Is eta x 1 minus eta 1 minus x, right? So that means actually you can write it, this belongs to exponential family. So that is actually what? X log eta 1 minus eta plus log minus or plus, right? 1 minus eta. That's it. So this is an exponential family, right? And now we can call this as a zeta because zeta is a natural parameter corresponding to as the coefficient of bx, right? And so then eta is what? Eta is the mean parameter, and zeta is the natural parameter or canonical parameter. So that basically gives, and then so then this one is so now you can basically, because now we have a functional form of zeta as a function of eta, right? And so I can write to find the reverse transformation. So what is eta then? Eta is nothing but exponential of zeta divided by 1 plus exponential zeta, right? So this is basically the inverse transformation of this original. So this is basically the same thing, and then you can use that to construct, right? You insert here to compute the psi zeta, which is this one. Okay. So then basically you can see that, okay, E geodesic means the theta is linear. So this is a sigmoid. So eta S is this one. And M geodesic is the eta scale, right? Because it's a natural parameter. Sorry, mean parameter. So mean parameter is a mixture type distribution. Okay. So yeah. So you can check this Bernoulli. Well, actually, until you really work out with your hand, with this toy example, it's hard to understand directly. Just so you know. But anyway, so I already introduced the conjugate, right? So this is another way. Same thing I already introduced, but sometimes it's called the Legendre transformation. So chat you if you check YouTube with the keyword Legendre transformation, they have a very fancy graphical explanation. So nowadays it's really good time to study, to do research, because you have a lot of resources in the YouTube and everywhere, right? So as long as you have a curiosity and persistence, then everything you can do anything. Okay. Now let's move on to so now this is really exciting concept. So we want to do Pythagorean theorem.
So Jay,
Yeah.
so can you move one slides? So 13. So this precise star is a definition of convex conjugate, right? Because
Right.
yeah, this is a definition of convex
Right.
conjugate.
Right.
But early can you move?
Yeah, right. That's a good question. So
So
actually,
why?
right, I know. Sorry. Okay, not this one. Huh? Oh, here.
Yeah, here.
You're
Yeah,
right.
precise star. So this does not take the optimization, right?
Actually, same thing, because it's when you say this,
Mm.
so basically right, we given theta, we given eta, we fix theta. And how we fix theta? Because theta, so one way is just to maximize theta.
Uh-huh.
Okay, it's the same thing.
Okay.
Turns out that
Okay.
because this is a maximizer.
Oh, okay.
Yeah.
Okay.
But
Yeah, that's what I'm
you're
thinking.
right. So this is actually more formal, conventional definition of the convex conjugate function.
Mhm.
Okay. So now, so this is the most important part from now on. Everything I discussed so far is to introduce what I'm going to do here. So anyway, so this is everybody here. I understand that all know what Kullback-Leibler divergence is, which is this one. And this is actually in my class yesterday I covered this. Okay, and I already told that this is not really a distance, because you cannot really exchange. But third point is actually important, because this is actually my research goal. So my research goal is to generalize Kullback-Leibler, because Kullback-Leibler is just using one particular convex function. And I like to, so we can use more general convex function, and then you can do a lot of many interesting things with that. That requires understanding of Bregman divergence. So turns out that Kullback-Leibler is just a stable special case of Bregman divergence. And the ultimate goal is that we can show Pythagorean theorem with Bregman divergence so that we can define projection. And then because then Bregman divergence is very general in the sense that any strict convex function, using any strict convex function, you can create a Bregman divergence. So that means you can choose a particular one that really performs well for your specific research problem. That's will give a very powerful result. So that is so we'll hopefully I can cover that next week. So first one is 3-point identity. So because suppose we have a 3-point, so notice that this P doesn't have to be in the manifold. So I intentionally distinguish between the two, P and M. Okay, P is the whole space, whole space of property density function. M is a particular subspace with a structure in it. Okay, but this Kullback-Leibler divergence can be defined for the whole space, right? As long as it has density, you can compute, and turns out that you can obtain. So because this is actually, so this guy, for example, is just a difference of the two. This guy is difference of the two. This guy is just difference of the two, and then you basically there's some cancellation, and so then you have basically we have 4 terms, right? And so you can actually obtain this. This is simple algebra. You can check. Now, here's the main theorem. Okay, now we have a 3-point in P. Now let's construct, so given P and Q, right? Given P and Q. So P, Q, R. And we want to do some sort of orthogonality here. Okay, so that is the goal. And now let's consider some line between P and Q. Okay, so the line between P and Q should be M geodesic. So there's a M geodesic line. And then and from Q and R, let's consider E geodesic line. Okay.
Can I have one
Yeah, sure.
Even this PQR did not be in our manifold M, is it still a parametric function of theta? Only then we can use your define theta.
Yeah, right. So this is so theta. Okay, theta M is a space that we are interested in projection. And so actually something like this. So this M include Q and R, but not necessarily P.
And PQ or 3 are U in U.
Huh?
In the whole.
And then PQ are all in this P.
P, sorry.
Script P.
Script P. Yeah.
Then M geodesic is defined in manifold M, right?
M geodesic can be defined for any element in P. But E geodesic is defined only inside P, inside M.
So M geodesic can be outside on some manifold M?
Yeah, actually, there's okay. So this is actually your question. So, yeah. So whether this particular linear combination is still in this space.
No, my question is not that. Q and R is within M,
Okay,
we assumed,
right,
we can still define just complex combination of P and Q.
right.
It is just a definition, but do we can call this as M geodesic? Because M geodesic is only defined in manifold M. The P is not in manifold M.
That's very, very good question. My answer, okay. So here's actually this is E flat. Okay. Q and R belongs to E flat, and this is actually M flat. And this is so different submanifold. Okay? Okay, that's a good question. So right, okay. So currently I just pick 3 elements, right? And create a M geodesic for one pass and create E geodesic to another pass. Okay. And now the question is, what do you mean by that two geodesics are orthogonal at Q? Okay. So this is the condition, right? Because this is a tangent. This is another, right? Score function. And then this is basically, so because locally at Q, so in the L2 space Q, we know how to define orthogonality already, right? So this is this one. So we want to impose a condition, orthogonality condition, which is basically two tangent functions has a zero inner product. Okay, at Q. So at Q means that when T and S are all equal to 0. Okay. So that is the condition we want to impose to achieve the orthogonality, and then do some algebra. So you can actually easily check these two result, because this is just a line, right? Scalar combination, and so you can easily check this differentiation, and so plug in, right? Plug in and see how this equation 11 reduces to 2. Turns out that is this one. Okay, because that's not difficult, right? If this integration, this expectation has an integration with respect to Q, so this Q and this Q cancels, and then basically this guy is constant, and this, because these two are density functions, so equal, so then you have this one. So basically, and now here's the magic. The magic is this: if you look at equation 12, and compare with 3-point identity here. Okay. So this condition is equation 12. That is a magic. Okay. So see, right? Because we haven't seen that, equation 12 is the one. The real condition achieving the orthogonality of two tangent vectors, right? Scope functions. And turns out that this condition 12, so left side of this 12, equation 12 is exactly the last term in 3-point identity. So because that by equation, so if equation 12 holds, that means this guy is 0. That means this guy is 0. that means this is basically the Pythagorean theorem. So that is, so I haven't shown. So it's just like a if and only if we keep doing. So equation 11 is equivalent to equation 12. Equation 12 is equivalent to equation 13. But I didn't really prove whether equation 12 holds or not, right? Okay. Now this is just some technical part. And now let's take a look if Q and R belongs to the exponential family. Okay. So if Q and R belongs to the exponential family, then we have this form. Okay. And so this is the left-hand side of 12, right? Of 12. And now we basically can use this one, right? And then simplify. So the constant term disappears because because of the density is all equal to integration is equal to 1. So you actually obtain this. So that means how to make this guy equal to 0. So how to make this guy equal to 0? That is equal to 0 only when 14 holes. Okay. So that is what? That is basically you have an exponential family here. But P is given, okay? P is given, and you pick any point in R, and move R over in M, and then the particular Q point with the same expectation of P is the point that achieves the orthogonality. Okay, let me use. Actually, I have a graph. I'm very proud to have this graphic thanks to ChatGPT. Okay, so okay, so here's the same thing, right? So okay, you have a Q. Oh, so should be actually sorry, maybe in my notation should be R. Okay, so we want to do PQR, but not all Q, right? One particular Q satisfy this orthogonality. Okay. Then question is how to choose this particular Q. It should be M geodesic from P. So that means EP over PX should be equal to EQ. So P is fixed, right? The P is fixed. So that means I can choose particular Q in this E flat space. In this exponential family. That particular Q is the one that achieves the orthogonality. Okay. So that is the main thing. So therefore, the Pythagorean theorem 13 holds when Q satisfies 14. And QR belongs to the exponential family. So P can be anything. P doesn't have to be in the same exponential family. Okay. Okay. I think I will quick have a break, 1 minute break, because I need to bring an adapter. Okay, and maybe stop recording and pause recording. If you have a good textbook, then everybody can learn, right?
Yeah.
So it's better to do something earlier than others know the importance.
So because no one teach exponential distribution like this, right?
Oh, right. Actually, this is really important, which I recently recognized. So I think so the whole right. So that's why I keep saying that the information geometry is indeed the shortcut of all statistical techniques.
Okay.
Okay, we'll see.
Okay.
Maybe I'm too excited. I don't know. So okay. So another theorem is if PQR satisfy this, then turns out that uh, you can construct the geodesic, one geodesic. So basically, it's like this. If you have a PQR and found that this is orthogonal, right? That means any point here will be orthogonal too, right? As long as it's in this part, in this line, they are orthogonal. So that is basically the theory says. So this is basically you can write achieve this relationship. So as long as this is 0, then this will be 0. Okay. So now, so the whole point of using Pythagorean theorem is that we want to come up with a projection. Okay. So the projection is the real key concept in statistics, I'd say. And so, okay, now let's have a name. So the exponential family, we use ME, and this is another tangent space, another some manifold, which has the same M geodesic with a given P. So this is for particular P, you can consider all the distribution with the same expectation, right? And then basically the Pythagorean theorem says what this Pythagorean is saying is that okay, this Q should be the unique element in the intersection of the two spaces. Okay. So this is pretty much the kind of summarizing what we learned. And so now we because now we gonna put name for this each projection. So E projection is the projection onto the E flat space. So this is E flat, which is an exponential family. Okay. And then we already studied that the minimizer, right? So the minimizer Q. So I mean, so you change over R, right? Over you move R over the E flat space, and then the smallest one, right? The optimal one should satisfy the should be the M flat from the P. Okay, so this is the basically E projection, and so this is called E projection, or some literature is called I projection, information projection of P onto this E flat. Now, suppose I use p hat, empirical distribution. Then what is the E projection? If I choose p hat as an empirical distribution, the sample, okay, here, okay. So as I said, this is an exponential family. This is now suppose this is a p hat. P hat is nothing but the data. Okay. Then what is this point? This is nothing but the MLE. Because why? Because we know that this one should be M flat. So then the whatever, so my point is that the empirical distribution of the PXI, right? This is actually evaluated. If you use a sample point to evaluate the expectation, that is this one, sample expectation, okay? That is what? Expectation of Q star over B, X, okay? So that means you can use this one as a equation, square equation for obtaining theta hat. That is the MLE. Okay. So E projection is essentially is very close to the maximum likelihood estimation. So, right, that's why, see, look at this. If you look at this one is this. So that is what? This is actually a expectation of log likelihood evaluated at P. So that means if you choose P as an empirical distribution, then this is essentially a log likelihood function, right? Sample computed from your sample. So the minimizer of Kullback libellar from P hat is actually maximizer of the log likelihood function, which is MLE. And then this particular theta it uses the this maximization.
So Jay, this actually explanation of MLE go beyond the exponential family, right? So on this page, you do not require.
I see.
So for example, you KO divergence P given Q.
I see. Right.
So
That's right. So actually, MLE can be explained as a E projection, regardless of whether the some manifold is exponential family or not. It doesn't have to be. Is that your point, right?
yeah, right.
Yes, I agree. Yeah. But if it is indeed exponential family, then the 16, the result in 16 will satisfy. But otherwise, it's just MLE.
Mm-hmm.
Okay, thank you. Okay, so now, so basically, this is E projection. E projection means you fix first component. So this is a fixed, right? This is a variable to be determined. To be optimized, right? I mean, maximized or minimized, whatever. Optimized. Second component. That is the E. Second component is to be chosen. Now, let's do, what about the other one, right? So if second component is given and try to maximize or optimize the first component, that is called M projection. Okay. P is given. You want to choose Q over some space. Then this is called M projection. Okay. And so there's some theory, I mean, mathematical, some details when the minimizer exists and unique and things like that, but I'm not really an expert on this. Okay. And now what is interesting, what we are interested, so the space, right? The Q is a subspace, submanifold. And the submanifold that we are interested in particularly is a moment condition. This is M flat, right? Mixture coordinate. Why this is actually very critically important for us, because in statistics, moment constraint is very important thing. So like a calibration weighting. So you can view as a calibration weighting as an M projection eventually. So the whole techniques that we learned in 521 could be viewed this way, minimizing this M projection. So you can change this guy later. You can change this objective function more general, different way. But the point is that the subspace that you are projecting on should be in the M space, M flat space, because the many statistical models, semi-parametric statistical models actually takes this form. Okay. And now the main result is this. Result is you have if you have M flat, so this is a different version of Pythagorean theorem. Previously, this result is different from the result for E projection, because here P is given here, right? The first component is given, but here this is fixed, right? Given or fixed. So we need a different algebra. Okay. And proof is actually different. So this part is the same. This part is the same. But we want to make this second, right? So goal is to make this one equal to 0, right? This is what we want. This is the goal. And turns out that the solution what? The M projection here, okay? So this M projection is actually M projection with this moment constraint is what? Constraint optimization problem, okay? So this is a very typical constraint optimization problem. And so if the solution turns out to be this form. So that's what you're going to show. And how to show this uses some kind of a Kuntakot theorem. This is a constraint optimization problem. So basically, see, optimization problem 17. Okay, let's write down what exactly is this problem is, 17. So you can write 17 as something like this. Minimize this one, right? This is a Kullback-Leibler. Subject to two constraint, right? So this is normalization constraint. This is moment constraint. And solve. So using Lagrange multiplier. and then turns out that the solution is this. So if the solution is obtained, this one basically means that this solution is this form. Okay, so we are done basically. But how to solve this one requires some technical knowledge, something like Kato derivative and things like that. So you can take a look, but this is some details. But basically, I kind of already show that this M projection is indeed a constraint optimization problem, and that gives us some another version of the Pythagorean theorem. Okay.
So, Jay, for this M projection, can you go to the previous page? Yeah, here. So in the previous part, so we have like a space that we want to project on,
Mhm.
right? So which means we just find the projection point from any point outside the space. So here we still have this space, right? Or we do not have this space to project on. Is that
Q is a subspace. Q.
but the
Small,
Q is not the space that we try to project on.
no, we do. This is the projection. I mean, what do I mean by that? So
But the KO divergence, if it's projected on, so we should fix the first argument and optimize the second one.
that
And
is
the second one, P is within a subspace. But here is it's kind of reverse.
right. So we are talking about reverse projection.
Reverse projection.
So this is indeed some reverse I projection. So that's why you call it M projection, right?
Mhm.
So M projection is a reverse projection.
Yeah, P is given.
Yeah,
And find the Q.
P is given, and then try to optimize Q. But it should be there's a constraint. So Q should belong to constraint.
Mm.
So different, right? So in the E projection, actually, if you write the E projection, I see your point. So in the E projection, this guy belongs to the subspace that you are projecting on. But here,
Right.
actually, this guy, right? Q belongs to the subspace. That's the difference. So in the E projection, right? So in the E projection, this guy is outside, and then so we want to find something inside.
Right.
That is E projection. But M projection is different, right? So M projection actually is inside the projection. So this is actually this projection. In this space, what is this one?
Mm. But the P may not be within Q.
So yeah, I mean, this is P. Yeah, P, and so Q. So Q changes over, and Q star should be here. But projection should be inside. So this is actually M flat.
Mm.
So actually, I can use this graph actually. So basically, this is projection. This is the original E projection, right? This is M projection.
Mm.
Okay. It's like if you remember the calibration problem,
Yeah.
right? I mean, you can do either one way is this one, dual is this way.
Okay.
So okay, I think that's it actually, and the others are all these are more technical part. So I will just skip, but you can take a look. Yeah. But the main message is about M projection and E projection and M projection. And then next week, so I will next week we'll move on to Bregman divergence and try to show this same E projection and M projection. I mean, discuss the Pythagorean theorem with that. Okay.
So Jay, essentially, because we just give a parametric example, but
Right.
if we are talking about empirical likelihood, then can you go back to your
Yeah,
graph?
this is actually so yeah.
Yeah, can you go back to your graph? Yeah, here. So if we are talking about the empirical likelihood, then that space, that ME space is a space that gave the moment constraint.
Yeah, ME
Right.
is actually yeah. So this is actually I'd say this is the moment constraint. Okay, so this is the actually space where M flat. So you have an M flat space where the moment condition holds, and then this projection gives the parametric form.
Right. I'm talking about um, um, uh, the the empirical likelihood without parametric form.
Well, it's the same thing. So basically, yeah, I can explain next class. So this actually gives the so actually the weight. So if you think of this calibration weight space, okay,
Mhm.
then the solution is actually is more like exponential lambda 0, omega 0, lambda prime xi, exponential tilting class.
Yeah.
Okay, so Kullback-Leibler gives the exponential tilting.
Uh-huh.
So Kullback-Leibler. So M projection gives the model, and E projection gives the solution. So basically, using M projection gives the dual form. I mean, the parametric form of your distribution. And then how to compute the parameter is actually E projection, because you can actually use the sample to compute the determine the parameter.
Yeah.
Okay. So it's exactly same thing that we studied with the calibration problem. So
Yeah.
in the calibration problem, we discussed the basically M flat space, right? And then try to project. And then what we did is using the Kullback, using the KK Kuntaka theorem, we got a parametric form,
Yeah, sure.
right? And so then the actual value of parameter will be computed from the constraint, calibration constraint. So it's actually the same thing.
Yeah. Yeah. So we probably are talking about the same thing.
Yeah,
Yeah, because I'm thinking that the ME, so that subspace is giving those moment constraints,
right, right.
so which that we need to find the dual parameter to
Right,
satisfy.
right. That's right. Yeah,
And your M flat is basically determined by the distance you choose, the divergence you choose. That implies a parametric model.
right. Yes,
Mhm.
yes. Well, actually, E flat. So E flat. So M flat is a moment. So it doesn't really changes with with the divergence measure that you use.
Mhm.
But the E flat changes with the divergence measure.
Mm.
Okay. So which basically means the parametric form of your weight.
Yeah.
Okay. So I think that's pretty much all today. So I think this is a quite intense intense seminar, but hopefully you guys learn.
But we will have to see with the introduction, we are getting the weight form. And using approximate
waveform, right? Form of the wave, a parametric form of the wave, and then E projection, you right.
We are getting the estimate of weight. Sorry, lambda.
Right.
That is
Right.
parametric.
Right. That's right. Yeah.
We are doing both things in the.
Yeah. Right. So that is, yeah. So that's why the information projection is very powerful. In even in survey sampling.
Thank you.
Yeah. Survey sampling.
Yeah, thank you, Jay, very much.
Okay. Well. Okay. Have a good trip to China.
Yeah, thank you, Jay. Yeah,
Bye.
bye bye.